Ji, Assalamualaikum and welcome to the 14th lecture, which will be mostly about practice problems in the third module of the course. So, as I mentioned before, we have done first two modules of the course were signal basics and then system basics. We talked about classification of signals and systems, and we talked about basic operations, basic types of systems, all that. And after that, we went into discrete time systems, in time domain. Yes, and there we actually discrete time signals and systems in time domain. And here we rewrote some of the signals, the common signals, the unit step, delta, exponential. We discussed how they look in discrete time. And we also looked at what do system properties look like in discrete time, the LTI systems, and all that. And all of that we were doing in time domain. And we answered a very important question for discrete time systems in this module, which was, if you know that a discrete time system is LTI and the input is xn, what is the output? Yes, output, how do you model the output of a discrete time LTI system? So we concluded that what we needed for LTI systems was to give it a nudge, an impulse, call the response an impulse response, and that impulse response will then help us answer this question in the way that we saw it would be a convolution of the input with the impulse response. That was it. Yes, and after that we spent some time understanding what these two concepts would mean, the convolution and impulse response. Why these two? Because these two were the ones giving us the output. Yeah, together the convolution operation with the input and the impulse response give us the output. So we were able to model this for LTI system, a very powerful model. I've discussed this in great detail in the previous 2 or 3 lectures. And now mostly we want to wrap up on what we were discussing in terms of impulse response. Just a few more statements or results, and then we move on to some practice problems for this module. Now, after this, the next module that we will go into will actually be discrete time signals and systems in frequency domain, where we will actually look into Laplace transform, or first maybe Z transform. So I'll see, but anyway it will be discrete time signals and systems in the frequency domain. So that will be the next thing we will be doing. So now let's see. We are here and we want to just wrap up the last part of the impulse response discussion and then do some practice problems. We've been doing some during the lectures also, but this session is mostly dedicated to that thing. So now the impulse response of a LTI system does not only help you give the output of the system to an arbitrary input, it can also help you characterize the system. So let's say it's established that this is an LTI system, and let's say you know its impulse response. Then you already know that the output to any arbitrary input is then simply xn, the input, convolved with hn. Yes, but then for LTI system, hen can also be used, hn, for characterizing the system in different ways. If you remember, in the second module we characterize the systems, we try to classify them, is it linear or not, is it time invariant or not. What else did we do? We talked about, is it stable or not, is it causal, is it memoryless. So for the general case, whatever we did here, causal, memoryless, stable, we did that for general systems, not just for LTI. So what we covered before was for the broad class of systems. Yeah, but today we will briefly see how you can do or these characterizations for LTI systems using only HN. So all of these can be done for discrete time LTI systems using HN. So the general one, we had the general results, and then for LTI, how do you do it? So firstly, what was a causal system? We discussed in great detail. A general causal system, we said, was such that the output, let's say yn, is a function of, for this, it's a function of, let's say, current and past values only. Yeah, doesn't have to be function of all of them, but no future value should show up. If xn plus 1 shows up here, then the system is no longer causal. Yeah, that was the general case. Whereas for memoryless, it was required that the system should just be a function, the output should just be a function of the current input, not past, not future. Yeah, so as soon as a past or future value shows up, the system becomes a memory or dynamic system. So we did that in great detail, and for general systems we did not restrict ourselves to LTI at that time. We were talking about any kind of system. Similarly, for stability, we covered Bibo stability, which said that if you give a bounded input, that means that if xn is less or equal to some mx, which is not infinity, then the output is also bounded. If you can prove that less or equal to some other bound my, which is not infinity. So this was Bibo stability, bounded input, bounded output stability, and we did that also. These definitions or these tests apply to the whole class of systems, all of them. They are general definitions. But now we will see the power of the impulse response. Not only it gives you the output to an arbitrary input, but also for LTI systems, it can help you very simply answer these questions. Yeah, so we will see that. First, I'm going to summarize it here, and then we will build what that is. So, for the system to be causal, we require that the impulse response Hn should be equal to 0 for n less or equal to 0, less than 0. Secondly, for memoryless, we require that Hn should be equal to 0 for n not equal to 0. So it should actually be a delta, can be scale delta. Sometimes we say that for this Hn is actually some k delta n. Yeah, k is some constant. So that will meet this definition. The Bibo stability boils down to checking the sum of the absolute values of the impulse response over all n. If this sum turns out to be finite, less than infinity, then the LTI system is Bibo stable. Here I am just summarizing. Causality test for any general system, very general definition. But for an LTI system, just look at, if you know its impulse response, just look at the impulse response. Is it 0 for n less than 0? Yes, the system is causal. Similarly here and here. Now, where do these come from? Yeah, that is what we just briefly want to look at. Where is it coming from? Let's see. This is here for general system. Now we have written the output as a convolution, and as we know, our convolution is commutative, so we can write it in different ways. I will write it in a way that will help us understand where are these coming from. So this is summation over k hk xn minus k. That's one way. Other way is to say xk times hn minus k, because convolution is commutative, both lead to the same result. But here this one is more instructive, so we'll write it like that. Now if we expand this out, let's expand this. Yeah, so let's see what do we get here. Somewhere in the middle you expect some h0 x n. Yes, if you put k equal to 0, you're talking about h0 x n minus 0, which is x n. And then to the left you would expect h minus 1 x, so just put minus 1 here, so this would become x n plus 1. Similarly here we will have some h minus 2 x n plus 2, because there is a minus, so minus minus will become plus, and so on, depending on what is the size here. On the right of that you expect to see h1 x n minus 1 plus h2 x n minus 2, and so on, depending on the size. Now this is the output. Yeah, so let's apply the general definitions of causality, memoryless, stability on this output now. And that is our output. Yes, so firstly notice that where is the current input, which term represents the current input. If it is yn, y3, then x3, so yn xn, this is the current input. What about these? xn plus 2, xn plus 1. At yn, these are future inputs from point of view of the output at n, whereas from the same point of view these are past. These terms depend on past inputs. Yes, whereas these terms depend on future inputs, and this is the current input. So at y3, x3, whereas this becomes x4, future, and this becomes x2, past. So it's relevant or with reference to this end here. Yeah, but now notice, if we apply the general definition, remember, we don't, let's say we don't know this yet, we're trying to develop this, get to this point. Yeah, so if we are getting to this point, let's see, for causality, which part, which terms should disappear? That is what we have to see. Yeah, which of these terms should disappear in the output for this system to be causal? Now, causality says that you should not have any terms which are future input values. Where do the future input values show up? Here. Now, how do you make them zero? Yeah, how do you make them disappear? You cannot require the input itself to be zero. So what you have in your control from a system point of view, the part of the system, are these, the impulse responses at -1, -2, so on. So if these happen to be 0, then all the future values disappear, and the output is not a function of any future values anymore. Yeah, so because of that we say, okay, an LTI system is causal if Hn is 0 for n less than 0. So for h minus 1 is 0, h minus 2 is 0. If you get an impulse response where, if you plot the impulse response to the left of 0, all the taps, all the values of the impulse response are 0, then you are looking at a causal LTI system. Now, by the same understanding, we can see, okay, what's required to make it memoryless. Memoryless says the output should not be a function of any future or past value. It is more restrictive than causality. So what has to disappear? Now, the future values have to disappear and the past values have to disappear. Again, you cannot force the input to be something specific. Input is given by the user or the situation. What you are looking at is the system. You're not looking at this input itself. Yeah. So the system contributes this impulse responses. What we do is we say, okay, let's take away h1, h2 if they are also 0. Then all the past values will also disappear. So this is 0, this is 0. If that happens, then whatever the input you give, the future values will be multiplied by zeros, the past values will be multiplied by zeros, meaning they will vanish, and the output yn will only be a function of the current input. That means only h0 should be non-zero, which we are saying that hn equals 0 for n not equal to 0, meaning for n1 it should be 0, for n2 it should be 0, for n minus 1 it should be 0, for n equal to minus 2 it should be 0. Only at h0 it can have some value, which means it's basically a delta function at 0, delta n, with some scaling. Whatever the scaling is doesn't matter for us. Yeah. So with the help of this expression, we have shown that the causality, which had this general definition, for LTI it boils down to, it simplifies to checking the impulse response. Is it 0 or less than 0 or not? So for instance, let's say you are told that a system has impulse response that looks like this. Okay, so at n equals 0, 1 and 2, it has some these values. Yeah, let's say you are given this hn. Now is this, and you're told this is from an LTI system. So then is this LTI system stable? We haven't done stability yet, sorry. Is this system causal? Is it memoryless? Yeah. So what do you see? Let's check memorylessness. What's the requirement for memorylessness? Memoryless says that hn should only be non-zero at n equal to 0. But it has values at other points also. It's not a simple delta. Yes. So it is not memoryless. It is a memory system. The second question we ask is this system causal or not? Yeah. So for causality, we require that hn should be 0 for n less than 0. Now n less than 0 is here, and notice it is 0 for all n less than 0. There is no value here. Yes. So remember, in discrete time, when we plot most of these 0 values, we don't plot them. We just assume they are all zeros. That's why they are not drawn here. So they're all 0. It satisfies the condition of a memoryless, of a causal system. So we will do more examples for that, but let's do the last one, which had to do with causality. With stability. So let's see. What would be the test for stability? I've already written that there, but let's derive that test. It is quite an interesting thing. So as before, let's start with the general test. Let's say that we send in a bounded input. So we assume that the input is bounded. Xn is less or equal to mx, which is less than infinity. Then if the system is LTI, then the absolute of the output simply has to be the convolution, yes, that we have been doing, hk x n minus k. So the absolute of the output is the absolute of the convolution of the input and the impulse response. Now I claim that this can be written as, this is less or equal to this guy, h k x n minus k. So what's changed here? What have we changed? This was the absolute of the sum. Now we have absolute separated and the sum is here. So the summation is done after taking the absolute. Yeah. why would that be greater, why would this term be greater or equal to this term? So I'll let you think about that. Of course, basically, if you think about it, what's happening is this sum can have negative terms. Those negative terms can make this sum smaller. Yes. Whereas in this sum, there are no negative terms because you took the absolute first, then you summed. Yeah. So the negative terms, even if they were gonna be there, they will become positive, and that is why there will be no cancellations. So this has to be greater or equal. If they were all positive terms, then the two will be equal. But if there were gonna be some negative terms here, then the right hand side is definitely bigger than that. Yes. So because of that, we say okay, that is fine. This right hand side is greater. But then we go further. We say okay, what happens if we replace the input everywhere by its maximum value? So we don't care about what value is. This is xn minus 1, xn minus 2, xn plus 1, xn. We don't say what the values are. Yeah. So if xn is like this, yes, we say okay, let's take the maximum value, the mx, and put that in place of these guys. Then whatever you get will definitely be greater or equal to this term, because you have replaced all the values of x by the maximum possible value of x. Yes. So you get something that is greater or equal to this thing. Okay. Now, assuming that mx is, we know that mx is a positive number. It's the upper limit of the absolute, so it has to be a positive number. So then this boils down to saying that basically this is a constant mx. It can be taken out of the summation, and what you're left with is this thing, summation, sum of the absolute values of hk. Yes, mx times this. Now for this to be not infinity, for this to be less than infinity, what do we require? We already know that mx is bounded. So basically xn is bounded by mx, that is the bound. It is not infinity, so we know this is a finite term. The only thing that can make this product infinite if this summation here is infinite. If this summation is finite, the whole product will also be finite. So the only condition left for the output to be finite is the absolute sum of the absolute of the impulse response should be finite, which we wrote here in using a different dummy variable h, and that's fine, doesn't matter. Yeah. So that is where this test comes from. So the previous example that I gave, where let's say you are told that an LTI system has an impulse response that looks like this, 1, 1, 2. Yeah, at n equal to 0, 1, 2. Is this system stable? Yeah. Now, just looking at the impulse response of the LTI system, all you need to check is the sum of the absolute of each of these finite or not. This test here. Yeah. So what is the sum of? You don't need to do it, but just for our interest, we say okay, h of 0 absolute plus h of 1 absolute plus h of 2 absolute. The rest are already 0. We say what is that? This turns out to be 1 plus 1 plus 2. It is 4, which is definitely a finite number. So you wouldn't really have to do it all the time. You could just see from here. Okay. So from there you can tell easily if the system is bibostable or not. Okay. So next we will solve some practice problems for the various topics that we have already done in this third module, which was discrete time signals and systems in time domain. So we did some practice problems for convolution. Let's add some more here for the sake of practice. So the first problem is this. Let's consider a DT LTI system. So we are given a DT LTI system, and we are given that its input is 1, 0 for n between 1 and 6, and 0 otherwise. These are integers, and the Hn, the impulse response of the LTI system, is also given. It is 2, 0, and n is between -2 and 1 and 0 otherwise. And we are asked to find the output of the, so we are told that this is a discrete time LTI system. The system has this impulse response, and the input given to the system is this one. And we are asked to find what is the output of the system. Now we know the output is simply a convolution. And then, as I mentioned in the previous lecture, and we practiced a bit, convolution we do through computers, MATLAB, other softwares. We can do through tables and analytically through properties, and we can do graphically as an instructive tool. So let's start with the graphic method, and for that we covered one method, which was the tape method. Yes, so let's do that very quickly. Now what was the first step in the tape method? You write out the signal, the input signal, and the impulse response. And what you need to do is make sure that you align them at 0. So let's see. Now the if I write the input signal, the input signal is basically 6 steps. So the input signal is 1, 1, 1, 1, 1, 2, 3, 4, 1, 1. 6 steps. But where is 0? You have to draw an arrow on 0, so you know where is the 0. Now 0 value is not given. It is 0 actually. This is 1. N equals 1, n equals 2, n equals 3. Yes? So because we need the 0 value, we will add another cell here and we'll put a 0 there. Now we can point to the 0. Okay? Last time what we did, we already had a value at 0, so we had that pointer. But if you don't have it, no problem, just add zeros until you see the 0 value. So now if you read this, what is it saying? The arrow tells you that this is value at n equals 0. So we are saying this is x0, this is x1, x2, x3, x4, x5, x6. Yes? After that it becomes 0. Yeah? Before that it's also 0. We needed 1 0 here to identify the pivot here. What about the impulse response now? Now if we look at it, the impulse response is actually has a value of 2 at -2, -1, 0 and 1. So we already know that 0 is here. Because we have put an arrow here. So let's put the value of h0. This should be the value here, should be x0, whatever that is. And here we need to put h0. So h0 is 2. After that we have h1, which is also 2. And before that we have h minus 1, which is also 2. And then h minus 2, which is also 2. So basically we have written out both the signal and the impulse response now, making sure that we align them at 0. h0 aligns with x0. It's shown by the arrow here. Yeah. Now what was the first step after that? So firstly, write them properly on a tape, aligning the zeros, aligning x0 with h0. Yeah, these two have to be aligned. After that, the first step was to flip one of them. Let's say we decide to flip x, and then if you do flip it, basically flip it along the pivot, so you should be able to see that this would look much like, let's see, this 0 1 1 1 1 1 2 3 4 5 6. Yes, this is the flipped one. Okay, after that, what you do, because it's pivoted at 0, it's flipped for the first time, the output, the first output you're getting now is y0. Okay, when you just started, what you do is you do multiply the overlapping cells and sum what you get, like we did last time. So we will do 2 times 0 plus 2 times 1 plus 2 times 1. This will be 4. So 2 times 0 plus 2 times 1 plus 2 times 1. This is 4. Now shift the signal one step to the right. Yeah. So next step is to shift our signal one step to the right. So there, there. Let's see. If you have shifted it one step to the right, it's 0 1 1 1 1 1 2 3 4 5 6. Yeah. So now this is why it's called a sliding tape. You write it on a tape and then you slide it. Yeah. Now since you have shifted 1 unit to the right, you are actually talking about y1. Again, do the same thing. Multiply the overlapping cells. Yes. And sum the results. So it's 2 times 0 plus 2 times 1 plus 2 times 1 plus 2 times 1. So I also got a 6 here. Now how long will this go on? You shift again by 1 unit, you get y2. Then again by 1 unit, y3. You keep doing that until all of this input, the overlap ends. When the overlap ends, you start getting zeros. So no need to go further. But there is an interesting here. You could also get a y minus 1 in this case. Remember, we shifted to the right. Yes, so we got y1, y2, like that. If you shift to the left, yeah, you should be able to get y minus 1. If you shift to the left again, you should be able to get y minus 2. But if you shift a third time, there will be no overlap. So you should be able to get a y minus 2, y minus 1, y0, y1, y2, and so on, maybe up to around y6. You will see, you get the idea. And that is how we do the sliding tape method. Now, this is instructive, but you don't always have to do it like this unless you are told to do it through a sliding tape method. You could also do it with, let's say, just using the definition of convolution. So what is the definition of convolution? We by now know that it is, let's say, k is minus infinity to infinity, or overall k, x, k, h, and minus k. Yes. Now from here you can directly try to solve it. You say, okay, what would y0 be? Well, y0 would be overall k, x, k, h. Remember, what becomes 0? Not the k. You are making n 0. So n will be 0. So you are talking about h minus k. Yeah. Now if you want to write it out a little bit, you will notice that this is actually can be written, there are other terms, but because they are zeros, so we don't really need them. X minus 2 h 2, yeah, plus x minus 1 h1 plus x0 h0 plus x1. there is a pattern to it, so once you see the pattern, it will become faster to do it, plus x2 h minus 2, and so on. Now you will notice that the H2 is 0, doesn't exist, yes, because Hn is between -2 and 1, so H2 is 0, it disappears. Yeah. H1, what is H1? Well, we do have H1, which is 1. We do have H0, which is 1. So like this, now you will also put in X0, X1 and so on, and you will see that you will actually get 4. But notice this is a bit more cumbersome. The graphical sliding tape method did this thing very elegantly. Yeah, so you will get the same answer, but it's more instructive, more elegant to use the sliding tape method. So let's see. Let's try another case. Let's say that you are, this is a second example, again a DT LTI system. So you're given a DT LTI system whose impulse response is given in terms of step functions. That's fine. And we say that the input is 0.7 n un. Okay. Now you're asked several things. Firstly, you're asked to sketch, let's say, HL. It usually helps, by the way. Even if you're not asked, I highly recommend that you try to sketch the input. Get a feeling for, don't try to make the exact sketch. Get an approximate sketch of the input and the impulse response. It helps a lot. So let's say you have to sketch Hn. If you are a bit confused about how to do this, simply use your knowledge of the unit step in discrete time. For example, this unit step, by now you should be able to identify that it is actually a unit step that starts at n equals, so this is 0, -1, -2. Yeah, so this unit step starts at -2. Now remember, un equals 1 for n greater or equal to 0 and 0 otherwise. That's the definition. So that by that definition, un minus k would be 1 for n greater or equal to k, yes, or 0 otherwise. So you should be able to, and we have done this before. So where does it go? Okay, then from there on it keeps going as ones. Yeah, it's all ones. So it's a unit step that starts at -2. Yeah, and all values are 1. This is the first term. Then minus the second one. Now where does the second one start? By now you should know, or you can try from here. N minus 2, it will be n greater or equal to 2. Yeah, so it actually starts at 2. So if 0 is here, our 0, 1, 2. So this guy starts at 2. Same height, by the way. So 1, 1, 1, 1. Goes on, all ones here. Yeah. Subtract these pointwise. Yeah. So what do you get? Basically, if you subtract them, -2, nothing to subtract here, so -2 will show up as it is. At -2 there will be a 1. At -1 there will be a 1. At 0, nothing to subtract again, so again a 1. At 1, again nothing to subtract, again a 1, so this is -1, 0 and 1. But from 2, 0, 1, 2, 3 and so on. Yeah, notice from 2 onwards there will be 1 minus 1. This is a minus. Yeah, 1 minus 1 for n equal to 3 also. So they will all be subtracted out, and this is your impulse response. Yeah, this is the impulse response that you were asked to sketch. Now let's say you're asked to find the output. Yeah, so again, in this kind of problems, the tape method may not be very useful because the input is kind of keeps going. It's hard to draw such a big tape. The impulse response, yes, it's just 4 values, but the input is a unit step multiplied by 0.7 n. Yeah, so it's kind of a unit step that is decaying, but it keeps on going. The input keeps on going. Yeah, so then it may be slightly hard. You could try to get some values, but it will be hard to get any general formula for that. So because of that, maybe we will go for the basic definition. So yn, we know that it has to be the convolution of hk x n minus k. Yeah, now notice this is k is minus infinity to infinity. Sometimes I write k overall k, yeah, but that's fine. But notice now, do you have to solve this whole thing? You have to solve all the terms or look for all the terms. If you're smart and look at it very carefully, you will see that for what values of k is hk non-zero? See, h is 0 for all the values from -3 onwards, and here from 2 onwards. H is 0. So you don't need those terms. So k can be limited. Instead of worrying about all the terms, k can be only from -2 to 1. -2 to 1. Because all the other terms, hk is 0. h3 is 0, h minus 3 is 0, h2 is 0, h4 is 0, h minus 9 is 0. All these terms here and here are all zeros. So you will limit your summation terms, yeah, according to what values you have. And in that range, what do we know about hk in this range? So h minus 2, h minus 1, h0, h1. What are the values of h in this range? From here we know they are all ones. So you can simply replace this with ones. So that essentially means that the output is basically k equals -2 to 1. Whatever the input is shifted by n minus k. Now what is the input? If this is the input xn, then xn minus k would be 0.7 n minus k, u n minus k. Wherever the n appears, replace it by n minus k because of this thing. So the output is 0.7 n minus k, u n minus k. And then we can just write this out for, these are only 4 terms. Yes, so we can write this out for the 4 terms and find different values here. Yeah, so I will leave it as an exercise for you to try to find those values. It's a very simple thing. Just expand it to 4 terms for k equal to -2, k equals -1, k0, k1. Yeah, just expand it and see what values you get, and you will start seeing some pattern there, and that will be the solution. Right, so what if now we are asked something additional here? Let's say we are also asked to say if this system, this LTI system, is it stable or not? Now we could go back to the very general definition of bibostability, but as I've already mentioned, for LTI systems, if you know the impulse response, a better thing to do often is to just check stability from the impulse response. Now for LTI system, bibostability means that the impulse response, absolute sum of the impulse response must be finite over all n. Yeah. So quick guesses, you can already start guessing. This is your Hn. Yes. What do you expect its absolute sum to be? This is a 1 here, 1 here, 1 here, 1 here. The absolute sum will be 1 plus 1 plus 1 plus 1. That's a 4. Yeah, it's very easy to see. So that sum is actually finite. So you could just write it out or mention that here. So you could say, okay, this is actually, it exists only at h minus 2, at h minus 1, at h0, and at h1. Yes, the rest of the terms are zeros. Yeah. So then all I have to do is say, okay, this is 1 plus 1 plus 1 plus 1 equals 4, which is not infinity, it's a finite number. So the system is, this LTI system, based on the impulse response test, is stable, stable. Okay, what if you're asked that this is it causal or not? So what are the guesses? Again, you could apply general definition of causality, but it would be wiser if you know that it's an LTI system and you know its impulse response, then just apply the result for impulse response. A DT-LTI system is causal if Hn equals 0 for n less than 0. Yes, now it's very obvious here that Hn is not equal to 0 for n less than 0. For example, h minus 2 is not 0. Yeah, even if in one point, in one place, this condition is violated, the system is not causal. Now, this system, in our case, this condition is violated because we see that h minus 1 is not equal to 0. Yeah, so that condition is violated already. And from the graph, it's always very easier to see. If you see any values to the left of the 0, the origin, then the system is not causal because it will definitely fail this test. Yeah, so the test becomes easy. What about memoryless? Now, since we have a result that says a DT-LTI system is memoryless if Hn equals k delta n, where k is some constant, meaning the Hn should look like an impulse at n equal to 0. Now, does this look like an impulse to you at n equal to 0? No. Yeah, the impulse at n equal to 0 would have to look like this. This is n equal to 0. Whatever the value it has is fine, but this is what we require. It should be 0 everywhere else. Yeah, since it doesn't have this shape, it's very different. Yeah? It doesn't satisfy the condition for memorylessness in a DT-LTI system. So this is not memoryless, or it's a memory system. Yeah. So notice that we did all those tests this time using the impulse response, and that's a very powerful thing. An LTI system can be characterized extensively using its impulse response. You can find the output, you can say if the system is stable, you can say if the system is memoryless, you can say if the system is causal. There are other tests also that you can do, but for now that would be what we are focusing on. Right, so let's let's continue with this kind of thing and do a third example. So this is a third example. You are again given a DT-LTI system where Hn is 1 by 3 delta n. Excuse me. So you are given a DT-LTI system and its impulse response is given to you is delta n minus 2 plus delta n minus 1 plus delta n minus 2. and you're asked, okay, first to plot the impulse response. So sketch HN. As I said, even if you're not asked to sketch it, it's a good idea to do that because visually there is a lot of information in there. So let's do that first. What is the sketch here? By now you should know that delta n equals 1 at n equals 0. So this delta n contributes a1, but then it's multiplied by 1 by 3. So it's an impulse, it's a unit sample here, yes, at n equal to 0. This one contributes its delta n at n minus 1 equals 0, meaning n equal to 1. So this guy contributes another 1 by 3, 1 times 1 by 3 at 1, and this guy contributes another 1 by 3. So basically at n equal to 0, 1 and 2, the impulse response is 1 by 3, 1 by 3, 1 by 3. That is the sketch of your impulse response. Now you are asked to find the output to a general input. Let's say there is some input, any input. What is the output? So, well, we know that the output has to be a convolution of the input and the impulse response. Yes. Now here is the tricky thing, very interesting thing. You're not given the input signal, yeah, but you can start thinking about what's going on here. Notice we know that the convolution is distributive, so you could have it as xn convolved with delta n by 3. I'm writing these three terms, plus delta n minus 1 by 3 plus delta n minus 2 by 3. Yes, and that is going to give us, now because convolution, as I mentioned, we sometimes solve through properties and then tables, yeah. Because convolution is distributive, it is like saying that it is xn convolved with delta n by 3 plus xn convolved with delta n minus 1 by 3 plus xn convolved with delta n minus 2 by the same thing, but anyway, by 3. Now we know another property of convolution, which was that we said delta is an identity of convolution. Remember, so we had said that xn convolved with delta n is back to xn. That gives us a hint here. This is xn by 3 plus xn. Now this one, delta n minus 1. If you check the tables, there is a shifting property also. And the shifting property simply says that this will become xn minus 1. So we are using properties and tables together to get to this result. Okay, so basically this system is behaving as it is taking three values of the input and averaging them, basically dividing them by 3. Yeah, this is the output or the general output of the system. Now let's say we are asked, is this system memoryless? Yeah, so let's see that also. Should be very easy to answer by now. Is it memoryless? Well, something wrong here, but anyway, memoryless. Yeah. So what was the requirement for memoryless? Hn should be a delta function at n equal to 0. This is not it. Yeah, there is a scaling here, but this is not 0 here. These should disappear for the system to be memoryless. That's the characteristic that we have, or the test that we have discussed. So since that is not the case, this is not a memoryless system. What about, so we will say since Hn is not like a delta at n equal to 0, another way of saying it is that what we require from memory-lessness is that hn equals 0 for n not equal to 0. But in our case, this test fails. So we can say, okay, the test fails because h2 is actually 1 by 3, which fails this test. Yes. So then this is not a memoryless system. What about causality? Is it causal? Again, what is the test for causality for LTI? Hn should be equal to 0 for n less than 0. To the left of the origin, Hn should be 0. You can already see that is true. Yeah. So yes, the system is causal. What about stability? Is it bibostable? Again, what's the test? We say, okay, the sum of all the values of the impulse response, absolute of their impulse values, should not be infinite. Now it's very easy to see. There are only three terms, 1 by 3 plus 1 by 3 plus 1 by 3, that is 1. So 1 is definitely a finite number. So the system is clearly bibostable. Now let's look at one last example before we close this. Let's say we are given a DT-LTI system whose impulse response is 0.5 n/un, and we are asked, is this system bibostable or not? Okay, so that's all we are asked. Now we're told it's a DT-LTI system, and we're asked, is it bibostable or not? So let's see. Again, what is the general test of bibostability for LTI systems? It is that for overall n, this summation absolute should not be infinite. So let's do that here. This over all n summation 0.5 n/un should be less than infinity. Now this is an interesting result. Notice un, what is un? So how does this look, by the way? If you plot it, you will see, because un is 0 for n less than 0, the left hand side is all 0. On the right hand side, you have a decaying function because of this 0.5 n. It is decaying fast like that. So what we can do is we can say, okay, we need n only over 0 to infinity. Yes, why? Because for n less than 0, this factor is all zeros, so they will disappear, and you are left with, and this is a positive number, so you are left with 0.5 n. Agreed? So you'll have to just think about what happened here. You were saying for all n, but then we realized that for n less than 0, this unit step will make everything 0. That's how unit step works in this case, yeah. So you're left with only 0.5 n, as long as you say that the terms are n equals 0 to infinity. So you adjust the terms. Now, is this less than infinity or not? That's the question we want to ask ourselves, yeah. So here we will make use of something we have covered in earlier courses, series. Yes, you know what's the sum of a geometric series? So basically, if r is less than 1, if it's a fraction, yes, between -1 and 1 is less than 1, then we know for n equal to 0 to infinity, the sum of this series is 1 upon a minus r. Okay, this is a known result in geometric series. So do we have that situation? Yes. What is our a? There is no a here, so it's a 1. It's a product of 1. Yes. R is 0.5, which satisfies this condition. So we can use this result. Now, if we can use this result, then we are talking about 1 over, because 1 over a for us is a 1, minus r, which is 0.5, and if you solve this, you will see that it is 2, which is not infinity. So sometimes we need to use other mathematical results to conclude whether an LTI system is stable or not. Yeah. So this was kind of a quick practice session related to what we learned in the third module. Yes, and we did some examples during the lectures also, but these will also help you. And if you do the quizzes, assignments, and other practice problems, keeping this knowledge in mind, you'll be in a good shape to perform well. Thank you.